So now we're going to do some examples of how to sketch graphs of rational functions. So the first thing I've got is a rational function, right? We can see all this. What we are going to need to do is identify all the appropriate features. Now, key things we're going to need to know are the zeros, vertical asymptotes, horizontal asymptote, oblique asymptote. Now remember, horizontal and oblique, if one happens, the other cannot happen. And then any removable discontinuities are also going to be useful. Now in this case, this graph has some of these features, but not all. Now looking at this, we see no common factors, that is, nothing that would cancel out. So there are no removable discontinuities. This is x squared, if you multiply it out. This is x cubed, which means it's not going to have an oblique asymptote because it is going to be 2x squared. Remember, I'm just concerned about the highest degree. What I'm looking for here. So when I put in infinity, I'm going to get 0, which means that this does have a horizontal asymptote at y equals 0. That's going to be important to the graph. It's got a bunch of zeros at -3 and 2, and then it's got a bunch of oblique asymptotes. So, or sorry, vertical asymptotes, my bad. -4, 1, and -7. Now, the key thing when we're doing this is we want to create sections of the graph, or pieces of the graph, that regions, if you will, that will help us kind of keep track of what's going on from one piece to the next. Right? I don't know why I did that, but what that means is we're going to split this graph into some regions, specifically regions that are marked by the vertical asymptotes. So the vertical asymptotes are at -4, let's call that right there, right? -7 and +1, right? So what that does is it splits the graph into regions, because these are points where, these are vertical lines where it's not going to cross. So in this case, I got 1, 2, 3, 4 regions of the graph I'm going to need to account for. Now, let's see what I've done to myself here. I also know the zeros, which are known points, are at -3 and 2. So at -3, the graph is equal to 0, and at +2, the graph is also equal to 0, right? That's going to be kind of important. Now I know the long-term behavior is it's heading towards y equals 0, so it's heading this way and this way, because that is the horizontal asymptote. What remains is to fill the rest of this in. Now, what you then also, and another point here that could be handy, is the y-intercept. Now if you were to look at this and distribute this out, at some point you'd have a 3 times the -2, which is -6 times a 2. So you have 2 times -6, which would be equal to -12. In other words, this would be the constant here. Here the constant would be these 4 taken together multiplied. So 4 times -1, or -4 times +7. So -4 times 7, or -28. Now this reduces to -6, -14, or it's going to be +3/7. Now 3/7 would be, if you plugged in 0, right, this would be what the y-intercept is. That is, you plug 0 in here, you get 0 plus 3, 0 minus 2, and that tells you what the y-intercept is, so 3/7. This is handy because it tells you about this graph. Now, please bear in mind this graph is only going to cross the axis at these 2 points. It's not going to cross at any others. Okay? So in this region, these 2 regions, these first 2 regions, it's not going to touch. So there's a simple test we can do. We're going to plug a point in, an x value, and see if it's positive or negative, and that'll tell us if it's going to be above or below. Okay? And then this, they've already decided for us. We know that must hit this point, and that's it. And then otherwise, it exhibits asymptotic behavior. So it's going to come down from down here, approaching the axis, come up through this point, come up through this point, and go like that. Okay? And then this one, it has a couple options. It could come from down here, go up, and then level off, or it could come from here, go down, come through, and then level off, right? Coming from positive, negative. So what we need to do is we need to plug in points. So what I'm going to do for this region is I'm going to plug in a point. Unfortunately, the only point I could plug in would be like -8. That's going to be a small one, right? So I could plug -8 in here, so I get 2 times -8 plus 3, and then -8 minus 2 over -8 plus 4, -8 minus minus 1. Now, before you get too panicky, I don't need to actually figure what these are. I just need to figure out the sign, right? So here's what happens. I end up with 2, which is going to be positive. Negative 8 plus 3 is going to be a negative number, times negative 8 minus 2 is going to be a negative number up top. Negative 8 plus 4 is another negative number. Negative 8 minus 1 is another negative number, right? So far, everything's canceled out, which means I'm looking at positive. But last but not least, I get negative 8 plus 7, which is a negative number. So what happens is I get net a negative, right? Negative, because I have 2 negatives, which will cancel these out, right? But then I still have another negative on the bottom, which means that this thing is coming from down here, because the value at negative 8 is negative, and then it's going to approach but not cross 0, like that. Okay? Same thing here. Pick a value so maybe like negative 5, and see what is the sign. So I'm going to plug negative 5 in here, so I'm going to have negative 5 plus 3, which is going to be a negative, negative 5 minus 2, which is going to be another negative, over negative 5 plus 1, which is negative, negative 5 minus 1, which is going to be also negative, but then negative 5 plus 7 is positive. So in the end, I end up with a net positive. The negatives cancel out, so I end up with a positive, so it's going to look something like that. Notice it's not going to touch the axis at all. Then last but not least, I test yet another point. Now, unfortunately, I need to test something like 1.5, because that's between here and here. I want to test a value here, so I know if it's approaching from down here or from up here. So I'm going to test out x equals 1.5. So 1.5 plus 3 is going to be positive. 1.5 minus 2 is going to be negative. 1.5 plus 4 is positive. 1.5 minus 1 is still positive. 1.5 plus 7 is positive. So what's my net? Negative, which means it's going to approach from down here, go up, and then come and level off. I agree it's going to cross the horizontal asymptote, but sometimes that happens. Okay. So the key thing is breaking this up into regions based on the vertical asymptotes, looking at the zeros and the y-intercept, right, as points that can help you figure out what's going on. Then push comes to shove, you have to test points. Now you're only worried about the signs, so notice I don't have to do any calculations except positive and negative. Okay? All right, let's try another example. Now looking at this, we have some zeros. And we have a vertical asymptote. We have no removable discontinuities. We do not have a horizontal asymptote, but we do have an oblique asymptote, so that's going to be a linear equation, right? Now, we're not too concerned. Now, if we're asked to find the characteristics, we're going to have to divide it, right? But if I'm looking at this, this is x squared over x, and the lead coefficient is 1. So I know in general it's going to be y equals x plus or minus something. But the key thing is y equals x, because that's going to tell us what the end behavior is going to be. X goes to positive or negative infinity. Y goes to, well, if it's a positive slope, it's going to go to positive infinity and negative infinity. That is, as x goes up, y goes up. As x goes down, y goes down. Okay? All right. So that tells us the end behavior. The only other thing is we want to figure out the y-intercept, which means we're going to look at the constant term on the top, which is negative 21. And then if you plug 0 in here, it's just going to be 2. So it is going to be negative 10.5, right? So now what we can do is we can sketch our graph, or start the sketch of our graph. We know we have one vertical asymptote at negative 2, right? So it's going to be a vertical line does not cross. We know it has zeros at negative 3, and positive 7. We know it has a y-intercept of negative 10.5. And we know that over the long haul, this thing is heading towards positive infinity and negative infinity. That's the oblique asymptote, right? So this is actually pretty straightforward. We know it's got to cross through this point, and head off that way, right? And it's also got to start down here because it's going to have to be negative, and something like that, right? Didn't get quite these to match up, but that's okay. here it's going to have to cross through this point, and that's it. Which means that it's going to come down here from negative infinity, and then come up just like that. So if you have enough points, then you can, and like I said, I'm not too concerned, you have to have these 2 points be accurate, right? But you can get the general shape. Try to indicate that, hey, we're heading off here, and it looks like, if you look at that, it looks kind of a linear equation like y equals x, right? One more example. Now looking at this, they're making you work for it, so always check to see if you can factor in case you can find some zeros, right? So in this case, the factors are 1 and 2. So the final form of this is this, factored. This helps us find the zeros, which are at x equals -2 and -1. The vertical asymptotes, which happen to be occurring at 1 and 3. There are no removable discontinuities, so we don't need to worry about that. The degree here, x squared, this is x squared, is the same. So that means it does have a horizontal asymptote, and that is at y equals 3/5, which means the end behavior is going to be the same, 3/5. We also need to figure out the y-intercept. That's going to be a useful feature. Conveniently enough, it's in polynomial form, then you put 0 and 0 in. This is going to be 6, right? So it's going to be 6 over, well, now don't forget your 5. If we distributed this out, this would be x minus 1 times x minus 3, right? So it would be 5 times x squared minus 6x plus 5. Then we distribute that, we give a 25. So it would be 6/25, or, well, that's 6/25, because you can't really reduce that. But we do care that it's a positive number and not very large. So, just like we've done before, we split our graph into some regions, specifically 3 regions. They're kind of close to each other, right? My best bet, right? Best stab at 8. So that would be at 1, and this would be at 3. We know it has zeros at -2 and -1. So the graph is actually here and here at -2 and -1. I think we're going to have this pinned down. We also know the y-intercept is at 6/25. Now please bear in mind this is not to scale. Okay. So the only thing, oh wait, we do know some of the end behavior. We do know the end behavior is 3/5. So we know over the long haul it's kind of headed here and here. All right. So we do need to test some points, unfortunately, because we're not quite sure what's going on. So if it's ending here, it means it's got to cross here and end up here. So over the long haul, it's got to come up there. It can't cross again. It's going to be positive, so it's got to know negative. It's going to hit kind of a, so it's going to end up coming like that, right? Now we know that this region here is going to be positive also, and it's never going to cross the axis, which means it's got to stay above the axis the whole time. So it's kind of like that. The only thing we need to do here is test, and I would recommend testing 2, right? By plugging 2 in and figuring out what the signs are. So if I plug 2 in, so x equals 2, my signs are going to be 2 plus 2, or positive, 2 plus 1, also positive, over 2 minus 1, which is positive, and then 2 minus 3, which is negative. So the net is that this is going to be negative. How does that help us? Well, it means that the graph is going to be below the axis, meaning the actual graph is going to be approaching here, coming up, hitting some value, and then like that. So that is the sketch. And by sketch, I mean sketch, but I have identified the x-intercepts and the y-intercepts as well as any asymptotes. This concludes our demonstration of how to graph a rational function.